who here really, if you'd be honest with me, right? Who thinks that estimation is really kind of a waste of time, right? You can be honest, right? And also it makes you feel better if you can raise your hand and feel honest about it, right? Almost everybody I talk to says that, right, in one way or another. And so, having developers make a wild-ass guess about something to hold them accountable to is not my idea of what estimation is. And so this isn't going to be a talk about all the diseases of enterprise estimation, of which there are many. I'll just say that, the patient is ill. I want to talk about what estimation actually is. So a simple rule of thumb to judge an estimation practice, just as a starting point, is that if an estimate doesn't help resolve uncertainty about a decision we have to make, then it doesn't have any value, okay? So that's like an easy way to start gauging what it is, whether we have something that's working or not. Our overall goal is to help you be a better software engineer by learning how to leverage uncertainty in estimation. That's where we're headed with this. So my name is Michael Godeck. I'm from a little town in Texas called Seguin that's just east of San Antonio. I started writing software back in the early days of the 8088 processor. And I currently work for this global pharma organization with thousands of websites in production and plenty of uncertainty that needs reducing. So about 30 years ago, one of the first consulting gigs I got when I stumbled into this trade was to build an estimation system for an electrical contractor, right? And my task was to implement their manual process and what they were calling in those days an electronic spreadsheet. And my client taught me his process. I sat down and went through his paperwork process, and then we modeled it in Borland Quattro Pro spreadsheets. And while I was working on that project, trying to unpack what estimation is about, there was a story in the news that made a big impression on me at the time, and it was the bankruptcy of the largest construction firm in the state of Vermont, where I was. That's in the northern U.S. I knew some of these guys. It was a family business. It went up in smoke over a single bid. Right? It was the Northfield Elementary School re-roofing project. And the estimator was an expert. He'd done a lot of these projects. He did his due diligence. He went up on the roof. He walked the roof, looked around before writing up his bid. But what he missed was really just how many times over the years that roof had been resurfaced with layers of tar and gravel, and it was all hidden below the surface that he couldn't see. And so the removal of the old roof was included in his fixed bid, and as it turned out, the cost of tearing up and removing the old layers of tar and gravel was worth more than their company was worth, right? It ran into the millions. And so ever since then, whenever I've been asked for an estimate, I can't help but think of that poor guy standing up there on the roof about to bring his company down. And I think Mark Twain had said, it's not what you don't know that'll hurt you, but what you know that ain't so. Right? In other words, your downfall is likely to be in assumptions that you didn't sufficiently explore. So I've been thinking about this for a long time, but it's only recently that I discovered this, how to leverage uncertainty in estimation, and that's what I wanted to share with you here. So as project managers and developers, we're routinely asked to navigate ambiguity, such as we're being asked to produce an estimate against some hazy business objectives or to make firm commitments against obviously changing scope, right? And I came across this quote recently from this guy, Kurt Kogel, I don't know. He said, the problem with estimating is that it's dependent upon having all of the facts ahead of time. Right, that was from an article in Cognitive World recent. So who agrees with that, right? That you can't have an estimate until you vanquish uncertainty, right? I don't agree with that view, right? I want to help you make uncertainty your friend in the process, because we have a lot of it in this trade. Uncertainty. So the first mistake we make in estimation is to ask for a single definite value. How long is this going to take? Is this 1 day? Is this 3 days? It sounds simple, but by asking for a discrete value, we start the pressure to look past the things that you don't know. You're the domain expert, right? You should know these things. How long is this going to take, right? So the imposter syndrome begins to set in, and you say, 3 days. But when working with discrete value estimates, we need to begin to understand how the implications of how assumptions are handled. It's our starting point. We expect that by the time the work's done, the actual cost and time is going to be different from the estimate, because we know that there's factors that we didn't know about and we can't control, which are going to affect the outcome. So as we estimate, we substitute the unknowns with assumptions about what they might turn out to be. So for example, you've got some third-party API. We've done a bunch of third-party APIs. This one looks like that one. We know there's risk, but we don't know where. It's supposed to be a RESTful API, but who knows, right? So when providing a discrete value estimate, we have this tendency, we increase the size of the estimate to accommodate our sense of uncertainty, and the size of increase becomes an implicit component of the estimate representing our assumption about the nature of some risk that we vaguely perceive. And when we inflate our estimate to accommodate risk and uncertainty, it becomes hard to know, what part of the estimate is how long we think it's going to take, and what part of it is like padding for the assumptions that we put in place that may or may not play out. So instead of lumping assumptions in with our effort estimates, we can make it easier to keep track of the risk and uncertainty by expressing our estimate as a range, which is a range that's most likely to contain the value. So the difference is significant because a range estimate allows you to quantify what you're uncertain about. Using range estimates gives us a much more powerful way to express uncertainty than bundled assumptions, because you don't have to commit to anything that you're not certain of, right? That's what the roofer did up there. He said, well, maybe there's more tar under there, but I'm going to say it looks like the other job, so that's what it is. The range and probability reflect your uncertainty. If you have no clue what you're supposed to be doing, if you can get past imposter syndrome, is just widen the range until it reflects what you actually do know, right? In contrast to tarballing your assumptions into a discrete estimate, the range makes your uncertainty evident, and it leaves it exposed for ongoing iterative reevaluation. So the essence of estimation is an iterative process of reducing your uncertainty about whatever it is you decide that matters. So reducing uncertainty is a question of first working out what you're uncertain about, right? That's decomposition. You break the question down, classify, compare, discriminate, distinguish, and so on, until you can reason about things independently, and then begin to ask what are the possible outcomes, what decisions would be affected by additional information. And as software engineers, we're good at this stuff, because when you actually do the work, you break it down into pieces until you eventually deliver it. I just want to back it up into the estimation process a bit. So for example, with this, one of the things you're uncertain about with this supposedly RESTful API that you're estimating is you've got to estimate how much time you're going to spend coding for errors. You expect to get back all 400 responses for errors, but you may wander into somebody's API where you've got a bunch of 200 responses with embedded error codes, and you're going to have a whole lot more time sorting through what really is an error and what isn't an error, right? And so instead of just adding a couple of days to that component of the work until you figure out what you're dealing with, you widen the range until you feel confident that the actual effort's going to fall in that range, regardless of how that question plays out. So range estimation doesn't have to take more time. You're just expressing things differently. If range estimation results in a greater comprehension of your uncertainty and you spend more time on estimation to reduce that uncertainty, then we'll take that as a good thing. If the actual uncertainty results in a range that's too wide for anybody's comfort, right? Again, if you can get past the imposter syndrome of making a guess that's unrealistic, then you need to figure out what questions, if you had the answers, would reduce your uncertainty. And reducing uncertainty is reduced by obtaining new information by means of observations about the questions that you've identified. When observations are expressed quantitatively, then that constitutes a measurement. Thus, a measurement is a quantitatively expressed reduction of uncertainty based on observations. So If that sounds like a mouthful, here's a more precise way of saying the same thing, right? This is from a 1948 paper called A Mathematical Theory of Communication. It's a fragment from that. It's by a Bell Labs researcher named Claude Shannon, who's really a giant in the industry that we're in today. Shannon postulated that information is the amount of uncertainty reduction in a signal. So Shannon's conception of information as uncertainty reduction, it was really fundamental to the emergence of what we know as information theory, the advent of signal processing, the development of integrated circuits, and all kinds of other things that we use every day today. So thinking of information as uncertainty reduction opens us up to a world of measurement where uncertain values are now first-class citizens. We're not trying to hide from things that we're uncertain about. We're bringing them to the surface, where we can consider more easily intangibles, which we once dismissed as things that weren't really subject to measurement, not subject to estimation. How could I know that? So Shannon referred to the reduction of uncertainty as the removal of entropy from the thing being measured relative to its prior state. An iterative process of uncertainty reduction increases the fidelity of the signal. So a definition of information entropy is the average amount of information conveyed by an event considering all of the possible outcomes. So if you have 2 coins to toss, the information entropy is the base 2 logarithm of the number of possible outcomes. So you've got 2 coins, 4 possible outcomes, 2 bits of entropy. And probably the stories you work on have more entropy than that. But the basic idea of information theory is that the more one knows about a topic, the less new information one is apt to get about it. That's the fidelity of the signal, right? The converse is what I refer to as leveraging uncertainty and estimation. And this is what everybody seems to miss, is that the less one knows about the possible outcome of a topic, the easier it is to obtain new information that might reduce that uncertainty. It's easier than you think to reduce uncertainty as long as you're not going through it for an absolute answer. So I'll walk through a little example here. Say you've got a story. You need to know how much time people spend in meetings during an average work week in order to figure out how to prioritize a story. What's the entropy of that question, right? So if you take everybody here at this conference, right, what's the average amount of time people spend in meetings? How would you know that? You don't know these people, right? How many people would you have to ask in order to get a statistically significant result? Would you have to ask 2/3 of the people, everybody, half of them? Right? What if we just walked out and asked 5 people at random? How much would that new information reduce the entropy of our question? What's the probability that the actual median of weekly meeting time for everybody here falls in a range bounded by the highest and lowest values in a random sample of 5? Right? So you might be guessing, right? The answer is it's greater than 90% probability that the actual median falls in a range bounded by a random sample of 5. It's the math of normal distribution. And the point is that when your prior state of uncertainty is great, such as this kind of example, then really a surprisingly small effort can yield a useful outcome in reducing uncertainty. And our measurement doesn't have to vanquish uncertainty in order to be valuable. It just needs to reduce it. So we didn't learn the actual average meeting time in a random sample of 5. We just learned a range that's likely to contain the median value, which is more than we knew before, and it becomes a baseline for our next cycle of inquiry. So when we quantify our uncertainty by expressing our estimate as a range, then we're saying we're confident that the actual value is going to fall somewhere in that range. And so you might reasonably be wondering, what we mean by confident. Because we could say with really great confidence that our task is going to take between a day and a year, and that would be like 100% confidence, and it wouldn't be helpful to anybody. To be useful, your range has to be in striking distance of reality, right? Not your 90% confidence, and again, it's the math of normal distribution. Having your actual value occasionally fall above or below your estimate range is what we need to know that your estimates are actually useful. And I'm going to touch on sources and bibliography where we can dive deeper on some of these questions. So we have this concept of estimation as uncertainty reduction, where we use ranges to model the fidelity of the signal. A tight range indicates a high fidelity, a wide range indicates a low fidelity. Working incrementally to resolve questions to reduce entropy. Each time we narrow our range based on new information, we increase the fidelity of our signal. A good estimate has a fidelity signal. Now, new information comes as observations, answers to questions that we express quantitatively. And mostly when we think about estimation, we're thinking about how much time is going to go into something or money. But we commonly use a lot of other scales to estimate, and it's important to know how and when to use them. You probably use these more intuitively than consciously, and I want to help you use them more consciously. So again, we'll go back in time, 1946. This is a couple of years before Claude Shannon's paper, A Mathematical Theory on Communication. There was this American psychologist named Stanley Smith Stevens, and he published this paper called On the Theory of Scales and Measurements. And so he defined a taxonomy of measurement methods. And you're familiar with them generally. He defined measurement scales of nominal, ordinal, rational, and interval scales. Right? So rational scales they're ordered sets that support addition, subtraction, multiplication, division, time and money, or rational scales you use every day. And you know you can roll up a time estimate into a single value, a bunch of time estimates, and you know that 2 times that value is twice as long, right? Rationals are really well known. Interval scales are ordered sets that are like rational scales, except there's no fixed zero, right? So the Celsius temperature scale is an interval scale, where 0 doesn't represent an absence of temperature. It's effectively an arbitrary point on the scale. So you're familiar with interval scales, but you may not know that the interval scale is the secret sauce of Scrum story points, right? Scrum story points make no sense outside of interval scale math. And so it's more than we can get into here, but suffices to say, if you're going to use story points, then you need to understand really the fundamentals of interval scales in order to be able to understand how your story points are working. And again, I can point you to material in the bibliography on that. Ordinal scales are very important, and we use them intuitively. We need to use them more consciously. They're ordered sets, but you don't know how much more one set member is than another. T-shirt sizes is an ordinal. Like Mohs scale of mineral hardness tells us that one rock is harder than another, but not by how much. So you can say granite's harder than sandstone, but the scale doesn't tell you anything about how much harder one set member is than another. And it's important to respect that attribute of ordinal scales. Think about the 5-star rating system. Is watching one 5-star movie as much fun as watching 5 1-star movies? Right? Roll-ups don't work in ordinals, but people do it all the time, right? You see it all the time in enterprise estimation. It makes no sense mathematically. T-shirt sizes are an ordinal scale that are typically conflated with a rational scale, right? Where people pin rational scale values on your ordinal scales, right? And so, again, it's like ignoring the properties of the measurement scales you're using actually tends to increase the ambiguity, right? Think about what it is, how it is you're using it. It's so common, this thing with T-shirt sizes and rational scales is so common. Alistair Cockburn devised an ordinal scale for backlog refinement to avoid this problem, right? We call it the Cockburn scale. And he just renames the set members to Cherry Pit, Peach Cobbler, Mustang, and Brontosaurus, right? So the Cockburn, everybody gets Cherry Pit, right? Nobody in their right mind is going to be sitting around trying to figure out how many peach cobblers fit in a Mustang. We don't know whether a Mustang is a horse or a car. It doesn't really matter. And Brontosaurus, there's no ambiguity. It's just any story that's too big to go into work. In backlog refinement, we don't need to know more than that. So it may seem whimsical, but the Cockburn scale makes little opportunity for conversion to rational scale time, and it keeps the focus on story decomposition where it belongs. And then we'll focus again on nominal scales, right? Nominal scales you use intuitively all the time. You need to use them more consciously in estimation. They're unordered sets of attributes. Essentially, you're testing for set membership. And having no quantitative value, you can't roll up nominals because each attribute is either true or false. Thus, nominal scales support making qualitative measurements. And there's as many nominal scales as there are qualities of things in the universe, so you have a lot to choose from, right? A really useful one that you may be familiar with is from Scrum is INVEST, which is just a set of attributes, right? It stands for, is the story, is it independent? Is it negotiable? Is it valuable? Is it estimable? Is it small? And is it testable, right? So a story should test positive for each one of those attributes before we allow it to go forward into technical planning. That's an estimate. When something screens for INVEST, that is an estimate. It doesn't have to, you don't have to say 3 days for it to be an estimate. So since nominal scales are testing for set membership, it's a binary question. It's either true or false, right? But our certainty about something is usually less than binary. So we can still quantify our uncertainty about binary questions by stating our confidence in a range of 50 to 100%, right? 50% confidence means I don't have any idea. Toss a coin. You can't be any less uncertain than that. So setting confidence intervals on binary questions helps us to identify what new information might increase our understanding of a work and makes our uncertainty explicit and persistent for reevaluation. So if we screen a story in, but we still have doubt about its testability, we know that we want to really ask more questions about testability as we go forward to make sure that, that we're not blindsided at the end. So the conception of a good estimate is a high fidelity signal. Estimating in ranges allows us to model signal fidelity and to concentrate on incrementally increasing signal fidelity by reducing uncertainty. We reduce uncertainty through observations, which we model quantitatively, and having a proper taxonomy of measurement methods and understanding how these measurement methods actually work. Choosing the right method, respecting the properties of the scale that we've selected are very important to be able to build your skills as a engineering estimator. But still, we only have a half an hour. Armed with all this information, probably next time you're back in backlog refinement thinking about this and the reality of what you're dealing with, you might feel like still a little bit lost. That's normal. What I want to do in this remaining part is lay out a roadmap of discussion of where it is that if we had more time, we could take this to build this out, because this is a conceptual view of estimation, and these principles apply to any area that you apply it to, but then there's a whole number of subsets of things that we need to talk about. The first thing would be, if we had another half an hour, I would be talking about practical techniques that you could take back into planning to help you adapt to range estimation. And the first one is the equivalent bet. And if you go to my website, michaelgodeck.com, there's a number more of these kind of techniques, and in the bibliography, I'll point you to some more. But just for this one, right? What we're going to do is we're going to validate your confidence interval by testing it against an equivalent bet. Right? There's a lot of research that indicates that betting with imaginary money is almost the same emotional impact as betting with real money. So imagine a carnival prize wheel that we spin, and it's got 10% slice in red and 90% of it in green. We're going to test your confidence in your stated estimate against a spin of the wheel. Right? Given a choice, which do you prefer? To win $1,000 if your estimate turns out to be in the range that you state, if the work ends up falling in your estimate, or to choose spinning the wheel and winning $1,000 if it lands in green, right? Most of us, really, when it comes down to it, the green is going to look more attractive. You have a better chance of winning by spinning the wheel. It's 90% green, for God's sakes, right? The point is that ideally you should be, that's expressing your overconfidence, you're underestimating. Your range actually should probably be wider in most cases to express your real 90% confidence interval that you can get this work done. And so you should widen the range, typically widen, sometimes reduce, until you feel ambivalent between a spin of the wheel and your stated range. It's a technique you can run in your head. It's very useful. There's many other techniques like this that can help you actually bring this into software engineering in a practical way. Calibration, right? Calibration is a procedure where you measure against a known quantity, so when it's applied against an unknown, you can have confidence in its observations. So we calibrate colors on screens, we calibrate tools, we can calibrate people too, right? When we calibrate people, it's a question of how to put you in touch with your own uncertainty about any question that you might ask, and we calibrate really through trivia. And all I can do at this point is to say, if we had another half an hour, we could talk about it. But I can point you to material in the bibliography where you can go into this question. But suffice it to say, humans are subject to so many biases that expert estimation alone will never be reliable. That's been proven in so many different problem domains, not just in software engineering and estimation, and calibration is actually part of the process to get to where we need to go. Decomposition, right? Right-sizing your story is one of the most critical team skills that there is. If you don't get decomposition right, you're going to have problems from estimation through to delivery to production. So the whole no estimates movement mostly is just, on the one side, an elaboration of all the diseases of enterprise estimation, and on the other side it's saying, let's just forget estimation and concentrate on story decomposition. Because if we get the story size right, then the work's going to flow. And so they're right, the heart is in the right place, but it is estimation. Decomposition is primarily qualitative estimation with nominal scales. All right? So we can get more formal about it. Queue time. Right? Queue time is a big problem in estimation. One thing you shouldn't do is be trying to bundle queue time into your estimates. People do that all the time. They say, well, it's going to be this much time, but it's going to be, for release, it's going to be pulled into testing and peer review, and it goes into the delivery pipeline. Separate queue time, just estimate the work alone, and don't take into consideration queue time. Queue time is important to estimate. We do need to know that. But it's a different problem. It's a problem of the system, not a problem of the work. By a problem of the system being your work delivery system, right? And they're different we use the same principles, but there's actually different techniques that you use to be able to estimate queue time and to look at the question of release planning, right? One of the problems in estimation is everybody's trying to bundle everything all at once. And so they start off saying, how long is the story going to take? But really what they're asking you is, when can I tell the customer this is going to be in production? And those are like a bunch of different independent steps. And if you try to do them all together, you're just guessing, right? And then finally, for those of you who are, where estimation means coming up with a budget for something, right? How much money to ask for something. That's project planning estimation. The principles are still the same. If you're doing parametric estimation and you're saying, this project looks a lot like all of these other projects we did, and so we're going to ask for this much money because we did that for those projects, you're a lot like that roofer, right? You're going to be right most of the time. But in the cases where you're totally wrong, you're not going to know until it's too late. That's the nature of parametric estimation. Parametric estimation is very good. I mean, it's useful, but it's dangerous, right? There's a lot of danger in just comparing large projects. We can use Monte Carlo simulations. Monte Carlos it's a branch of mathematics where we use repeated random sampling to obtain numerical results. You don't have to understand Monte Carlo math in order to do Monte Carlo simulations. You can build these out in spreadsheets. And as long as we can break things down into components that we can reason about independently, express them in ranges, then we can model complexity. You can model very, very complex projects into reasonable budgetary expectations using Monte Carlo simulations. But we need at least a half an hour to talk about that too. So finally, here's a bibliography of some of the sources that I went through in this presentation. If you're doing story points, Mike Cohen's Agile Estimating and Planning is where story points came from. I'm not a big fan of story points, but that's a basis for it. Queue time, go to Kanban, David Anderson's Kanban book. Steve McConnell's Demystifying the Black Art of Software Estimation is still a good book after all these years. Vasco Duarte's No Estimate ebook, his heart is in the right place. It's kind of confused, and it is estimation. It's not no estimation. But it's a good read, too. And then finally, Doug Hubbard's How to Measure Anything, Measuring the Intangibles in Business. It's not about software estimation, but it's really an awesome, awesome book in terms of bringing together a lot of these techniques. So I hope that moved us forward into the making estimation a discipline in software engineering instead of some kind of black magic. And if you think that I don't want to talk about this more, or you're wrong, I definitely want to engage more on this. We're going to set up something in the unconference for tomorrow about this time around noon. We can continue the conversation. Grab me. All my contact information is on my site, michaelgodeck.com, along with additional information about all of these and other topics. So thank you.